Hello, and this is my name is Ahmad, and doing the presentation on one of the projects I delivered to one of our clients. I'm working as a consultant, and I have worked with Asterix for many years, and and I have had other talks about Asterix, how I integrated, and this is more recently the project I delivered based on WebRTC. It's an ongoing process, but mainly it's tested and it's working. So I am based in Europe, in Norway, and most of our customers in Europe. So I want to tell you about these projects. Like, you know, the client basically had a full Cisco or Tamberg portfolio of the products, which covers that portfolio covers from switching servers to the endpoints, to recording, to multiplexing units, and they basically covered every product that Cisco introduced in telepresence area. The scope of this work was they want to expand their network, their telepresence network, with WebRTC. So there are options, and they can go with a. I'm just going to show you the diagram first. So the option would be this is the platform they have basically. What you see between the two firewalls is a DMZ zone, which is a video communication servers, which is called Video Communications Express. And the internal one, the cluster you see there, is a video communication controllers. And they do communicate and provide network traversal. And the endpoint inside the network, they can call to the internet, and the endpoint outside, they can register, they can call inside, and they can call outside. So there is a 4-port open between the two clusters through the firewall, and they do multiplexing through those 4 ports and establishing the communication. But the external one, they have to be open because the requirement for the media, it covers a long range of ports. But to securing the internal network and separating it from the external, the internet, we are required just 4 ports to be open. So that was I mean, there are more components, but I just simplify it just to show you the diagram in here for simplicity. Working with you know, proprietary equipment is like they have the downside that the API is closed. You have limited access of scripting and doing new things. You are bound to follow the instruction what is provided by the vendor. But apart from that, having said that, Tamberg or Cisco had the leading products in HD video communication area. So in this section, I'm just showing you another project that I delivered. This project was the client wanted. They had they had a full video infrastructure. What they wanted to have a voicemail and conference me, call transfer is on the voice side, not on the video side, because there are you know, calls coming from mobile phone or landline, and you know, they're calling directly to the endpoint, or they simply want to have a voice conferencing. The mobile phone and the landline, they are not capable of doing video conferencing. So the option, you know, the integration of the Asterisk, the Asterisk survey in there was the best choice, the very cost efficient, and you know, after doing a lot of testing, it worked very well with VCSS, video communication servers. There were some tweaking we have to do. We have to sign some development agreement to open up to get access to the API, which I don't know you can. Yeah, I don't have a pointer to show you, but the database on the VCS side, they basically closed. So to get access through API, you have to sign a non-disclosure or development agreement with a vendor. So basically, after doing that, opening and synchronizing the databases, the clustering of Asterisk server to make it redundant, done through having a front-end open SIP and distributing the incoming calls to each Asterisk boxes. So that project delivered very well and worked very well for the client. The other project that mainly you know, my focus is on this session is WebRTC and video. So I'm doing a little bit of comparison between video and WebRTC. The video side, the video equipment, the endpoints basically they are more capable of doing things. They got transcoding, they got like multiplexing, they can do error correction. They have very sophisticated sort of algorithm, you know, implemented in there, but it comes with a high price tag because, you know, well, of course you pay for the testing and you know, fully dedicated endpoint for that purpose. It's not like you installing just the software on a PC. But so yeah, as I said, they can deliver a full range of functionality based on, you know, dedicated hardware. The endpoint generally based design for the rooms, like, you know, if you order a T3 endpoint, it's like you basically waiting for a truck, you know, parking in front of the door, and they come with a crane and unload the equipment and install it for you. But there are a small version of it for the executive and, you know, for general staff at a lower price range. They have a software version. It's called Jabber that you can install on different OS, different operating systems. Less expensive, but it works well. It works very well with the rest of the platform. On the other side, the WebRTC is the most attractive things is you don't need to install anything, and it's basically free. It's you know, you can expand your network by many folds instantly. The challenge, of course, is like, you know, going through learning curve, how to do that, how to install it, how to get the WebRTC work. One of the challenges I had during working with WebRTC on Asterisk was like getting it to work. It was quite frustrating actually. It was you know, trial and error, a lot of things before you get it to work. The WebRTC basically is designed for peer-to-peer connection, and the signaling is kind of a you can consider as a cursed or a blessing. It's cursed because the interoperability is not defined, it's open to you to decide what sort of signaling you want to use. So it's like, you know, if you are a developer, then you can sit and write your own signaling system, signaling protocol. But on the other hand, if you want to communicate with other systems, with other video systems, then, you know, if you have many different systems that different developers sitting and working, and probably they just adopted like XMPP, I don't know, SIP, server event system. So they have to have a translation of or transcoding of those signals to get it to work with each other. And the last point was, so since, like, you know, the point-to-point is attractive, of course you establish a communication, but these days, like, people want to get into the conference and talk to each other. So WebRTC is not designed for that. You need some kind of multiplexing system, MCU or SFU, to do that functionality for you. So this, based on, if I wanted to you know, deliver the project for the client solely based on the Cisco product or Tamac product, it's I had to introduce two more components into the network. The first one is a CUCM, and the other one is called JabberGuest client. And doing that, I have to. Yeah, the pointer, I'm sorry, I cannot you know, show the pointer. I don't have a pointer, but the clusters you see there, that's the brain of the network. And by using Jabber client and CUCM, I have to change all the software installed on that, change the dial plan, change a lot of configuration just for the sake of having WebRTC working with the rest of the platform. And that comes with a high price tag from timing, from installation, network downside, testing. A lot of things has to be coordinated to deliver that. So a lot of changes has to occur on the network, in the network, to get one functionality established and expand the network and introduce WebRTC. The other option I decided to go with was using Asterisk. Using Asterisk is mainly I mean, you can use any other server like Node.js or any other server that capable of handling WebSocket or any other WebSocket protocol, but at the end is that you have to speak to the rest of the network, which is SIP-based. So the obvious option in this case was using Asterisk and integrating to the rest of the platform. As I mentioned, like, you know, it was a bit challenging to get WebRTC work with Asterisk. But you know, being patient and reading a lot of documents and, you know, trying, testing, and doing a lot of try and error, eventually I got it to work. But so yeah, in this case you can see for the internal I have one Asterisk box, and for the external in the DMZ I have another Asterisk box. So the external one using the DMZ box, and that box talks directly through the SIP trunk to the VCS cluster, Video Communication Server cluster. And the internal one does the same thing through another SIP trunk to the internal VCS cluster. So that was the whole concept of enabling WebRTC for the client, for bringing WebRTC into the existing video platform, which is basically was Cisco platform. And it worked well, and it was much cheaper option for the client, and no changes, no dramatic changes required, or dramatic changes of configuration of the server. Basically, you just establish a SIP trunk between the Asterisk and the video server, and the most of the work is on Asterisk and getting it configured to work with WebRTC, and basically you're separating the video system from the WebRTC side. So the rest of the things, I just wanted to do kind of a, take you through the learning curve I went through to learn the WebRTC and getting it to work with on Asterisk. So basically, with WebRTC solution, you need to consider five major things. Connecting the user, start signaling, finding an ICE candidate, and negotiating media sessions, and starting a RTC peer connection. So the first one, you can have different client, different browser sitting on different PCs. They have to meet. They have to know about each other. So you can have a web server. They all use the browser from that web server, so they are aware of each other. They exchange token through that web server, and that's the first one. It could be anything else. It could be Asterisk server. It could be Node.js server. It could be any other server. The point is, they know, they are aware of each other, and they can exchange token. When you pass that stage, then you come to exchanging signals. Okay, what we want to talk, what signaling we want to talk, what signaling, how we gonna talk to each other. There are options I listed there. There are many more that you can write your own one. As I said, like there is nothing defined in WebRTC from the signaling side, and is open to you to decide what to use. So in this case, I use SIP signaling, and then there comes that when you pass that stage, the third one is finding a candidate, finding an ICE candidate. So every PC these days, they have multiple networking card. Like you got blue card, you got Ethernet card, you got wireless card, and sometimes you got multiple wireless card. So through ICE and turn, you have to establish like where the endpoint is, what is the address, and what is the port allocated, and communicating to how the PC communicate to the network, through which device, through which network card. So the ICE framework basically using stand and turn to establish, like my PC, which card is getting to the network, what is the IP address of that card, and what is the port is used through the firewall to get to the network. So it does that for any other PC that trying to communicate with each other, and matching the devices, not necessarily the same thing, but matching, like mine, it would be like stun, and the other one from another PC would be a turn server that they can communicate with each other. And when you pass this stage, then it comes to the negotiation of the media. Okay, we establish like how we can talk, but what we're gonna talk. Let's say in WebRTC, you're bound by two protocols, VP8 and to H.264. So, but in video side, you got much more than that, 264, 265, 263 plus. But in this case, then you have to establish like what video protocol you're going to talk, what is the bitrate you're going to talk, at what bitrate, what is the resolution you can handle, all those codec-related issues that you talk through your STP sessions. And when you've done all those things, then start the API, WebRTC API, which is RTC peer connection, to transfer the information between two or three or many WebRTC sessions or browser. So the WebRTC APIs provided to us is basically three things: media streaming, RTCP peer connection, and RTCPD channel. So I don't need to read through it. You can have a look at it quickly. What is the purpose of each? And I just explained the second one to you. So when I started, like, first thing I wrote the code, it was on my PC, and like I have 2 sessions on the same PC, and it worked very well, and I was really happy. But in reality, when you want to do that, you have to test it between two different PCs, and they're not less, like first one, when you see it internally, they sit on the same subnet. Like, you go through the staging, the curving learning curve, and you go step by step. So the simplest is like, you think that, okay, if I have 2 WebRTC sessions on 2 PCs sitting on the same subnet, then it should work. And it didn't for me, because the PC got its firewall, and you haven't encountered that problem yet. But through reading logs and doing Wireshark capture and all those things, you come to learn like what is the error and try to resolve it. And the next stage, when you solve that, then it comes between different subnets. You have PCs on different subnets or different VLANs. So that would be another issue. But so these are the internal things. These are the internal network. But in real world, you don't sit next to your significant others on the couch, and you call them and says like, okay, can you make me a dinner? No. In reality, it's like you sitting in your office and you're trying to reach somebody the other side of the world, or you're trying to reach somebody at home. So it goes through the internet, and it comes the real challenge, which the other picture on the right shows. You go through firewalls, and the firewalls, as we know, there are 4 different types of firewalls. The most difficult and challenging one is the symmetric firewall, which changes the port every time you send a request out. And so basically, you need a stun and turn server. A stun is used for the signaling part. You're trying to find out what is my external IP address. If I send a packet out, what would be? And the stun server tells you what port you are using and what is the IP address. So put it on your SDP session when you're communicating to the significant others. And as I said, with a symmetric firewall, you cannot rely on the port number, because every time you send a request out, then the port number changes. So you need some intermediary server, like turn server, to relay the media to traverse the network for you, to traverse the firewall for you. So they are always in path to traverse the media through the firewalls for you. And the ICE, basically, which is a framework, is based on this, make it much faster to establish the common candidate device for you, for 2 endpoints to talk to each other. Yeah, I just mentioned that. And well, if ICE would usually takes long time, because they have to go, if you got several devices, they have to exchange ports and IP addresses, trying to understand which one is available and which one we can communicate. So it takes a long time. But there is another RFC called Trickle IC, which try to run that protocol or framework to establish what is the suitable port for you before even the communication starts. before you doing anything. So I'm just showing you a simple code that, simple snippet of the code that how you use the turn and stun server there. Very basic. By a few lines, you can use that and use the ICE protocol, not protocol, framework. So as I mentioned, WebRTC is designed for peer-to-peer connection, but we are interested sitting in the room and talking to each other, multiple participants sitting in the room and talking to each other and discussing things. And it comes to the bottleneck of, okay, can we do WebRTC without having any multiplexing system? Is that viable choice for us? Well, when we tested, looks like, with at least my PC is I consider it as a good PC. It's the latest one. It's got not lots of RAM, but good CPU and good graphic. And when we tested it, it can handle eight sessions at a time. And we tested with other PCs, and that was low even. With eight sessions, you could get roughly good quality results. But when you go beyond that, then it's the picture get a little bit blurry and not good quality. You won't get a good quality of the things of the video. So as you can see, after signaling, you create a mesh. If you don't have a multiplexer, you create a mesh between all those WebRTC sessions. And that means for every single device you're trying to communicate, you open a video stream, and that requires CPU, they require memory, and it requires bandwidth. If you got 2 megabit bandwidth available to you through to your PC, wireless or whatever, then 8 sessions would be very low quality. So to resolve that, either you have to limit the number of participants, or you have to limit the bandwidth for each participant, or the best way is using an MCU. That's from my point of view is the best option to go with. You have to have use MCU or SFU because WebRTC is basically not designed for that purpose, not designed for multiple participants. These are I got some links for you if you're interested to look up, if you want to get your started on WebRTC. I don't know if you're already working and exporting WebRTC, but as I said, I just wanted to inform you about my Kerbin experience, my learning curve experience, and these are the things I thought it's good starting point if you want to get your hands dirty with WebRTC. And this is the last slide for me. Yeah, so if you have any questions, I'm happy to answer. Okay, so we all clear, I guess. Thank you. Thank you for attending.